please use the Q&A. With that said, I'll pass over to Tim Martel. So just with a little bit of explanation here, if you're not familiar with Tim already, Tim is a program manager for the AECB Standards and Certification Scheme, and he's an expert advisor for the RIBA Retrofit course. And he also is the principal author of PHribbon, which includes, of course, embodied carbon calculations and the likes as well. Originally trained as an architectural technologist, Tim has been a Passivhaus Designer since 2012. So you're in good company, and you'll be well supported by everything that Tim's got to say. So over to you, Tim. Take it away and lead us through this session on the step-by-step approach.
Thanks very much. So I imagine we've got quite a diversity of people watching. We might have people who are familiar with Passivhaus, we might have people who are familiar with Carbon Light, but we might have people who are not really very familiar with either of those. So I'm going to pitch it so that everyone should be able to understand what we're talking about. And I'm going to start by defining a few terms. So firstly, is it called step one or is it called step by step? You might have heard both those terms. And really what we're talking about is Carbon Light Retrofit. The Carbon Light Retrofit is what it's called, is the name of the standard. But within that, there's an option, the step-by-step method. It could be done in a step-by-step way. And step one is the minimum permissible step. Because the step-by-step method, we don't tell people what the steps have to be, that may sound as if it leaves it very open. What we do define is what the minimum step has to be. So that's what step one is. Step one is, we'll come into that in a bit later, but that's what it is. And that's why it could be called step one or step by step. It's actually part of the same process. And if you've heard level one, well, that's because we did call it level one last year, but for a little while, but we're not anymore. Another thing that we're now, just another thing to qualify, is that you may have heard that the AECB has been talking about deep retrofit for quite a long time. In fact, it's been a really high priority. We've been talking about that for many years. Why are we now suggesting a step one method, which doesn't seem to include very much, if any, retrofit? Well, this is going to become apparent in the next few slides. But essentially, it's a good low carbon measure, and low carbon energy is expensive and disruptive to produce. So it's important to consider carbon as well as energy. Energy and carbon are both important, and we're going to go into that. Well, we're going to go into the carbon side of it. You might already be familiar with the energy side of it, but the demand side, we can't leave it completely. There's buildings are very, very wasteful the way they're built now in terms of energy efficiency. So there's certainly a big opportunity to improve things very dramatically there. One last thing that I'm just going to qualify is what's the difference between Carbon Light, and that's the AECB standard, and the Passivhaus and Retrofit standard. Those are both produced by the Passivhaus Institute. So the Retrofit is their retrofit standard. Well, there's a lot in common. First of all, there's the retrofit and new build standards are part of both, and they're both founded on the same building physics. They actually use the same tool, PHPP, which is the Passivhaus planning package, and there's a lot of commonality in terms of the comfort criteria, the building fabric approach, but where Passivhaus really focuses is on being a low energy standard, and it does actually reward levels of PV in terms of Classic and Passivhaus Plus, Passivhaus Premium. It names those levels according to how much PV you've managed to put on. So heat pumps are favored within the Passivhaus approach because you have to meet a primary energy or a primary energy renewable criteria. That's primary energy is the amount of energy that's required to make the energy that you use. So in the case of electricity, it's just over twice as much energy goes into the energy that you actually use when it gets to your house. But apart from that, they don't actually require or specify having heat pumps. Whereas with carbon light, it really sets out requirements for good design. That's what we're really all about. That includes energy efficiency. The design has to be healthy, it has to be low carbon, and there's reliability in there too. So we're going to elaborate on these terms. This is just to give you an overall picture, but energy efficiency is part of the criteria for the building fabric. There's ventilation and comfort criteria in the health side of it. Low carbon, well, we're going to see that in the next few slides. And reliability, well, that's all part of the QA process, which we're also going to look at as well. So I'm going to, enough of the introduction, I'm going to go into the main reason why we're talking about this possible divergence from using low energy. Why are we now talking about carbon? Why is step one quite a good approach from that side of things? So I'm going to do that with the help of a graph. And here, you won't see anything yet, but should now see, this is the tons of carbon produced by a semi-detached house. It's the total carbon CO2e, carbon equivalent, operational and embodied. And in this example, it's calculated with PHribbon, which is some software that the AECB uses, and for embodied and operational CO2. And for that reason, it covers all the CO2 from the space heating, the hot water, and a bit of the electric too. That's a large overview. Generally, we want to be talking about space heating, but in this overview, it aligns with PHribbon, and it shows you the context of the whole carbon story. So 194 tons for the gas boiler since point A, that's 60 years. That's A is the point where we might retrofit, and we'll see that here. If we do a full carbon light retrofit without an air source heat pump, we get a line that comes out like this. And let me just make sure my pointer is. There we are. So we can see little steps here, and those steps are repeated embodied CO2 from things that have to be replaced during the lifetime. And so that's full carbon retrofit. That's one of our retrofit standards. But in this case, it's without an air source heat pump, and that is a possibility in our standards. The next thing would be just to compare, what would Enefit look like? Well, Enefit can be done. This is the Passivhaus standard for retrofit. It can be done without an air source heat pump. It doesn't, because an air source heat pump isn't required. So this is a possibility. There's also another possibility that it's done with an air source heat pump, which will be in the lines below. But let's compare that with what would happen if you did a step one. If you did a step one without really doing a retrofit, you'd end up with the green line down here. And what that's showing is that even though we don't actually do much of a retrofit, because the carbon, the electricity we're using with a heat pump is so low carbon, it actually gives a very good result. And so we can broadly describe these two carbon light standards. The step one, we can think of that as really being the low carbon measure, and we can think of the full retrofit as being the affordable warmth or warm measure. Now, I know some of you might say, well, it's perfectly possible to heat a step one retrofit or a heat pump fitted house so it's nice and warm. Well, that's true, but if you turned it off, then it would. If you turn the heat pump off, then it would cool down quite quickly. So the intrinsic nature of the building is that it would be a warm building if you had a full retrofit, whereas it wouldn't really be in a step one. So that's what I mean. And so that's simplification. You could install the heat pump later if you did this if you did this full retrofit. So going up this line, you could, at point B, you could install an air source heat pump, and then you'd go along this line, which is a mirror of this line. You'd go along the same gradient as this route down here. It'd just be up here now instead. And what that would mean is that you still end up with, well, sort of some kind of mid-range outcome. And the sooner you can do that, the better. In fact, this option here, where you're primarily doing the retrofit, the full retrofit first, and then you're adding the heat pump, this leads to the mid-range option, but the mid-range outcome. But if you were to do the air source heat pump first, let's have a look at some measures which do that. Then now here the air source heat pump and the full retrofit are done. So there's a bit of embodied CO2 from that, and then you have the steps of the embodied CO2, but it ends up more or less the same place. Now this is with the air source heat pump, that was without, same thing. And you could also install the heat pump at C here. So we've already done the air source. Sorry, you could install you could do the retrofit, I'm sorry, at C. So I've said we install the air source heat pump at A. We go along this route here, which is the step one route. It stays like that for a few years. And then at some point later, maybe 17 years later, something like that, perhaps when the air source heat pump is ready for renewal, what we were thinking was maybe at that point, or possibly sooner, you have a full retrofit, and that would end up more or less the same place. Now, I should say that these graphs don't include the embodied CO2 of the huge investment in infrastructure that would be needed to put this, to make all this possible. So if everyone went for air source heat pumps without any retrofit, like a step one, then to make that possible all over the UK, there would have to be a massive extra facility of wind power, storage, whatever, all the transport, transmission lines that would be required to make that possible, and that would have an enormous, well, a fair influence on the embodied CO2 of the CO2 factor which you're using, and we haven't taken that into account, and it wouldn't be possible to take that into account without knowing how it was, how many people did that. So although that has an effect, we haven't included that. These calculations are from the viewpoint of the building. We can do carbon calculations for the building itself. If we take away just to simplify a little bit, if we take away the lines which aren't to do with carbon light, and we're still looking at the original house as well, then we can see that we've got down here the step one, which is the green one, and the carbon light full retrofit, there's two lines there with the heat pump, and then there's without a heat pump is up there. So it's actually fairly straightforward what we're talking about here. It's really low carbon, or it's possibly not so low carbon if you don't have it with an air source heat pump. And if we were to look at that in terms of what's been happening per year, now this graph is slightly different from the last graph in that the last graph was cumulative. This graph is showing what's happening a year. So whereas we've got the lines for gas here mean that we're still talking about carbon, but the lines for gas being the same, meaning that you've got producing about the same amount of CO2 for a gas boiler every year until you retrofit. At year 5, what happens was we install a heat pump, and you can see the embodied CO2 from that. That's this darker green area with a red background. And then you see the you see the operational CO2 from the electricity, this series of bars that are tailing off. That's showing you that the grid is decarbonizing and the CO2 factor is reducing over time. Then what happens is we thought at say 17 years or something, you would have the embodied CO2 of the full retrofit. That's what we've just been talking about. And then CO2 factor of the electricity is reduced even further, but it's smaller anyway because you don't need so much. And you have some further little steps here. And it may look as if this is really large and overwhelming, but let me just show you, go back to this graph before, that actually that was only really part of this little step here. So where we said, oh no, actually this little step here would be, wouldn't it? The retrofit there is not a huge amount. It looks significant on the other graph, but it's in the overall process over 60 years, it's not really a huge thing to be worrying about. Whereas the carbon factor, these do have an effect because there's so many of them. We're adding it up over 60 years. I wanted to describe a typical process, what's actually involved and why we, what are the components to this step 1 method. And I'm just going to do it by, we're starting with looking at the heating system of a typical house. So we're talking about gas, a gas boiler, and that's got to be matched with the radiators. And then just for context, I'm going to talk about, I'm just going to introduce it in terms of the full retrofit. So the gas boiler would go to a heat pump, and there'd be a possible resizing of the radiators, may not need to. And then you'd have the deeper fabric measures and ventilation. That would be the full retrofit. And I should really say that there is another way of doing that. There is a possibility that the heat pump, as we saw, isn't installed straight away, but you still have to have a plan for it later. So that's why this has gone to the end. That's a possible option as well. But going back to where we were, just talking about the full retrofit so that we can compare it with what happens with step 1. If we look at step 1 now and what that does, well, the heat pump has to be probably a bit bigger. The resizing of radiators, that's a bit more of a process. And the retrofit plan now becomes a future retrofit plan. So the step 1 is now really only 2 parts. There's certainly a little bit about of energy in there there's certainly a little bit of retrofit in there, but not a huge amount. And if we compare that with all the standards now, if we look at all of those together, we can see that they all really contain the same things. The heat pump is in all of them. It's either at the start or it's at the end. The possible resizing of radiators links to that. And the deeper fabric measures, well, they're either done at the start or the end, or they're a future retrofit plan. So it's all actually the same components, and that's why we still call it a carbon light retrofit. It's still all the same thing. It's got the same parts to it. These options just give you a different sequence of doing it, different possibilities of doing it. Just a brief look at the what a retrofit program might look like. We did do some stock modeling. In fact, I did some stock modeling just to think about how this process might work. And at the time, we were thinking that people might do a step one. There might be quite a lot of people just doing a step one because it's very affordable and easy to do, relatively easy to do. And a smaller number of people would do a full retrofit. And then some of the people who did the step one might later do the full retrofit. So this peak is the people who did the full retrofit straight away, and this peak is for those who have already done the step one and then decided to upgrade. Hopefully, we would like a lot of people to do that, but they may not, and they don't have to. And this would be the full future-proofed retrofit, that the full complement of all these things together that we just saw. Now, I want to go into a little bit of detail now about what's in the step-by-step method. And just as an introduction to that, now, I'm not expecting you to read this. All I'm expecting you to do is look at the green color. Because what I'm trying to point out here is we've got in these three columns all the three different standards that we've got. And what I'm trying to show you is, well, this is a step-by-step method, it's highlighted. But can you see here that this green bar here means that this part of it is shared with all the standards, and this part of it is shared with all the standards, and so is this. So this is the ventilation, this is the overheating, the thermal comfort in summer, and this is the air source heat pump where installed, the flow temperature. So there's continuity between the standards, and there's also some sequence, well, some graduation of the figures as well. You can see here the air tightness goes from 5 there. This is a Q50 figure, meters cubed per meter squared hour, 5, 2, and then 1.5. So there's continuity between the standards. But let's take them in little groups. What do we stand for with the carbon light retrofit? Well, the first thing we're interested in is it being low carbon, particularly in the case where I've just demonstrated about the carbon aspect of the step one. You're changing the heating system to a heat pump, and it has to be a low carbon, non-fossil fuel method. You can't not change it to a heat pump, because that's the very essence of the step one, But another part of that is that you have to also make sure that that heat pump is installed efficiently, and that means it has to be either less than 50 degrees C, that aligns with octaverse energy, or ideally less than 45 degrees C for the flow temperature. And another part of that is that the primary energy for the house has to be within sorry, there's no limit for the primary energy, but we are a little bit concerned about the primary energy anyway. So we don't allow direct electric heating for most houses. There may be a case where the certifiers allow it for multi-story dwellings as an exemption. But the primary energy, the reason we still got that is that it points out the issue with direct energy, direct electric. So that's the first thing, low carbon and some supporting criteria. Next thing is we have some criteria for the building being healthy. And the first one there is MEV or MVHR. And the design of that ventilation system, you could either use Part F or you could use PAS 2035, which is now free, by the way. And that may go a little bit beyond Part F. Another aspect of it is the air tightness, which is to minimize energy loss and drafts. Okay, that also bears on to the energy efficiency part of it as well. But notice it's a Q50. With Passivhaus, you tend to use, well, you use an N50 instead, which is air changes per hour. This is Q50. And why do we do that? Well, it's really for two reasons. To bring it in line with UK practice, which is in terms of Q50 instead. And it also places the emphasis on the building fabric quality. So it does mean that we're focusing on the bit that actually really matters. The next thing is the summer comfort. And the summer comfort is affected by a few things. The window design, the shading, the ventilation, and the building fabric. So it's a collection of lots of things, really. But it's an important aspect of the design, and we really don't want to have too much overheating. Less of a problem in this country, but still something, an issue that we have to address and can't avoid. So that's part of it as well. And fortunately, the Passivhaus planning package already has a criteria for that, which we can use, and we use the same rules as they do. Less than 10% is acceptable, but really best practice would be less than 3. And then the last part of this little collection would be the path to energy efficiency. Now, we can't say that the building has large energy efficiency components already built in, because that's yet to be done. That would be the medium-term improvement plan in the terms of in the language of the PAS 2035. But it is on the path to that, and that has been factored in to the whole process. In fact, you would improve the air tightness a bit further on that route. The heat pump running costs are considered here as well. In step 1, what we ask as a criteria is that the heat pump must cost less or the same to run than an equivalent, the previous heating system, which would have been, say, a gas boiler. And that safeguards the expense side for the occupier, makes sure that they're not actually going to be in a worse position. So that's quite a neat little part of our good design. It's also an automatic calculation, so you don't have to worry about where you're going to get the figures from. It's actually built into our Carbon Light certification spreadsheet, which is one of the things I manage. And to look at all those things together, let's see how they fit on the certificate. The final designer certificate is still being modified slightly, so this is the latest we've got to. And let's look at those things. Low carbon, that would be, we've got on the right hand side here, we've got a list of those points that we were making in terms of everyday language. And then the more technical side is in a table over here below the photo of the house. So first thing was low carbon. There's also low carbon crops up down here because we were talking about that in the context of primary energy. Helps keep that low carbon. The health criteria, they're mentioned here. They're also the overheating risk that comes up as a figure, and also the air tightness, which also is one of the energy efficiency things. That's the third thing we were talking about. And there's another, that's the energy efficiency, the third point we looked at. And then the other thing to say about this is that it also has the progress towards a full retrofit. In the context of a step-by-step, really, you could be anywhere in that process. So how do you show on the certificate how far you've got? You could be a minimum step. This has clearly got beyond the minimum step because we've not only got an air source heat pump, we've got an MVHR. You didn't have to have an MVHR. You could have had an MEV instead. And this has got, looks like the whole of the loft insulation. It's got some wall insulation, although there's some parts of it, of the process, not complete yet. So actually part of this is the walls at the back haven't been done. The windows at the back haven't been done. They've been done at the front, but we've also got floor insulation to do to actually get to that level that we need to for the full retrofit. And when we got a full retrofit, we could actually reissue a certificate and give them a certificate for that as well. At the moment, they're on the path because they've got a step-by-step certificate. If I was to show you, just for comparison, the new build one, then on that one, what's different is that we're not just on the path to energy efficiency, we are an energy efficient building. We're looking at all the fabric, walls, roof, floor, windows, all that's been done. You can see by the space heat demand that it's actually done an awful lot, 39 kilowatt hours per meter squared per annum. Another thing that's part of our reporting is that we provide standard reporting graphs, and these are very easy to use because they don't actually require any user input. Apart from this energy use intensity, you have to enter the GIFA because it's per meter squared of GIFA. You have to enter what that is. But apart from that, they're automatic. Even the operational CO2, that's done through the PHP. It doesn't use PHribbon. We're not requiring people to use that. It actually just modifies your PHP. So these tell a very interesting story. If we just pause to look at that for a moment, the space heat demand, we're looking at three different stages. The pre-retrofit, that's the existing house. The step one, which is the step that we're the minimum step, and then the full retrofit. So the full retrofit is a future phase, but right now we're in step one, and we can see that the space heating demand hasn't really changed. It's a little bit lower because we've added a little bit of insulation, but we haven't really added very much. And energy use intensity shows a similar story, looks a bit more of an improvement. The running cost, we did say that it has to be equivalent or slightly less, and it is. But it doesn't actually really improve until we do the full retrofit. And we can see with the operational CO2 that step one is a massive improvement in CO2, and the full retrofit is even more. So that's quite useful. And there are equivalent graphs for the other standards as well, but they rely on trying to find a comparison building or comparison figures. Whereas this, you've got all the comparisons built in because you've got the retrofit, you've got the pre-retrofit, you've got the step one, and you've got the future retrofit as well, all as energy models. Another part, we're coming towards the end, so we'll be able to go through some questions, but part of our quality assurance process is that we have photographs. And that means that we have to have some documentation. We've got documentation for our certifiers, elaborating on some of the issues they might come across. Certification is done through certifiers. It's not self-certifying anymore. And that's part of the quality assurance process. We have to have trained people who will recognize issues, will recognize and intercept them. And because one of the things about retrofit is that some particularly quite tricky issues can crop up, which might not be recognized to the unskilled person until it's a bit too late. That's part of the reason why we had PAS 2035, to make sure that as an industry that people are recognizing issues and resolving them very quickly. The guidance document there is shown there. There's also a guidance document for the images. That one there is for step 1, and there's another one that covers the full full retrofit and new build as well. Another thing we have is we'd like to be working with MCS installers. It's very likely we will be, because people get a grant of £7,500 towards the cost of an air source heat pump by going through an MCS installer. So it's very likely they would go through that route, and therefore it would be useful if we could produce data which will go into their calculations. They will want to use their own calculations. I think they have to, but we can take advantage of the modeling that's been done. And so the U values that were worked out in the building have been converted here. There's the ground one has to be converted so that it goes from normal PHribbon criteria to include the ground factor, which is more part of the UK methodology for ground-based U values. So that's part of that as well. There's more information on that in the questions if you want to ask that. So that's, I think we want to allow a bit of time for questions. So I wanted to just stop there and see if anyone has anything they want to clarify. There's plenty of extra that I can add, and maybe some slides that some questions you ask will be answered through other slides that I've got, but I wanted to open it up at that point.
Thanks, Tim. That's been a really great whistle-stop tour, shall we say, through the retrofit standard and how a step-by-step approach can be adopted and used and applied. And there have been a fantastic number of questions in the Q&A area. So I'll just lead you through. I've been trying to keep an eye out for them, looking for commonalities, and then we can just sort of tackle them.
I'm afraid I can't see any of them because I'm sharing my screen, but
yeah, we can tackle them en masse, as it were.
Good.
Where certain questions seem to have had duplicates. Yeah, so I'll just go through some of the quick headline questions, not in an order of priority or anything like that. But one of the questions that arose was, how can we use PHPP to model these step-by-step approaches? And I think that yeah, we've got a couple of approaches available to us, don't we?
Yeah. So they all get done by first producing a PHP, a Passivhaus planning package model, and that has to be done by an approved modeler. That's a qualification you can get from the AECB. It relies on, well, anyway, you can get a qualification from the AECB for that, and then it goes through a certifier. But the certifier will be using this other piece of software that links into the PHP. So the PHP is produced in a step 1. You have to have 3 PHPs. You have to have the initial house, the step itself, and then the retrofit, the full retrofit, a future scenario, which of course isn't done yet, but you have to look at the future. And then you bring them together with this Carbon Light standards spreadsheet, which reads all those, takes the information in, produces the graphs, produces the certificate, and also looks at all the other things that might need to be met, the things that might need for that certificate to be valid. and then brings it all together, and then you end up with you may have to go back and tweak a few little things, but then you can go back to your PHP and change those, and then update the Carbon Light spreadsheet as well. So it's a very standardized process, and that's one of the really neat things about this whole route, is that it's a very, very clear. How do you get to this standard that we've got? It's very, very clear, very easily recognizable steps, and a very solid QA process in doing it.
Yeah. Thanks, Tim. That's you can use PHP by building a series of models, or you could use the variants tool, both of which can be made to work with the plugin that Tim mentioned. And
those models are really just slight variations of the same thing, because they're
exactly. Yeah, this is it. A savvy PHP user, as you say, suitably trained and knowledgeable, will be able to deal with all of that with no problem at all. One of the underlying questions that's cropped up a number of times here relates to the modelling that you did, looking at the life cycle of these retrofits, and also whether those, in modelling that, whether you also took into account the fact that the grid is decarbonising over that life cycle, and
definitely
how that'll play out. Now, you did talk to some of that, but it's just to say there's been a few repeated questions on it, so I just wanted to give you the chance to explore that in a little bit more detail.
Yeah, you can see that the grid is decarbonising. Yes, I was taking into account that the grid is decarbonising, and we're using the grid decarbonisation factors that come from the future energy scenarios of the national grid, and they may revise those over time. They may, at the moment, they revise them every year, and we're going with their latest idea of what it might be. If it turns out that we all use heat pumps and we all need a huge amount of energy, then they'll have to revise it a little bit.
Yeah. No, that's it. And yeah, that's it. So you've used the most up-to-date information that's available.
Absolutely.
You've considered how the grid will decarbonize. There's always going to be certain amount of uncertainty in that. So therefore these are indicative trends, of course, rather than absolutes. But the key thing is that it's been broadly recognized. And on a similar sort of note, one of the questions that's cropped up a few times relates to the cost benefit, or the cost analysis, and how that is structured, in terms of understanding how the cost of a heat pump versus other costs may be used as a comparative model.
Oh yes, well the cost of so is the question about exactly how that's done in practice.
Yeah, so which assumptions are made about the costs? Because obviously we've had a very volatile market at the moment for fossil fuels, or for energy supplies. So the question has been kind of what assumptions are going into that.
Well, oh, sorry. Need to share my screen again, I think.
Now, you're sharing your screen. We can see your desktop at the moment.
Oh, you can. All right. Okay. Right. So let's go back into that.
So was it the national grid data that we're using? The regulator. I forget the right name now.
Just a second. Hang on. Oh well. Anyway. Yes. We were. Oh yeah. Here we are.
Yeah, the Ofgem. That's it. Yeah.
Ofgem. Yeah. So
you've used Ofgem data, so therefore we're independent of individual companies, and we're looking at.
That's right. We're using Ofgem data, and here you can see, for example, that well, we need 3 different models, so we've got 3 different columns. We've got baseline, step 1, and the full retrofit, and it just works out the delivered kilowatt hours. It's got the cost per unit, and you end up with a full cost there for the baseline, and the full cost for the step 1. I think there may need to be some discussion about whether the standing charge is included or how much of the standing charge is included.
Yeah.
That's a point I have to tweak within the next week or two,
Yeah.
a few weeks. But essentially, it's all done. That's how it works.
I think,
Sure.
Tim, it might be worth just explaining a little bit about why this particular criteria is so important, and also what it doesn't say. It doesn't tell you how much your bills will show, does it? Because we've standardized it.
No, but it safeguards the possibility that for the building occupier, that it safeguards the potential problem for them that they could be going into a low carbon building, but actually that is a lot more expensive to run for them, which probably wouldn't be a long-term thing that they're very happy about. So this is a very good thing about our standard, where we allow a heat pump to be installed. It has to be installed efficiently, and this is one of the criteria.
Yeah, I think there've been a good number of questions relating to heat pumps, and I think that we can kind of quite quickly scoot through some of them. The questions have arisen from will PHPP tell us whether we can achieve the 45 degrees Celsius flow temperature? That's one of that's one end of the spectrum. And then there's other ones of how can we guarantee, so to speak, the performance of the heat pumps, and the COPs. And I think that there's a lot of variables in there. And this is why working with the MCS installers and other accredited designers for the design and installation of heat pumps is so critical. There's only so much that we can do until we're in managing this process. But what have you got to say, Tim?
Well, the great thing about PHribbon is that you can model heat pumps in a lot of detail, and it actually works out as being really, really useful, because it allows you to take the climate region of your area and put in the heat pump that you're going to use and see actually what overall SCOP it gets. And that has to be done in a detailed way. You can get very rough figures from the manufacturer, but they don't know where in the country it's going to be. So they don't know really what the climate it's going to be installed in. So it makes a lot of difference by modeling the actual building, the actual heat pump, the actual climate. And that's what PHribbon does really, really well. And that's a really good base point to start with. And it has quite a big effect on the efficiency. But you asked if PHribbon is able to tell you what flow temperature you have to use. Was it you have to?
That was the question. That was the question. It was, can we use PHribbon to confirm that we've achieved the flow temperatures? And well, in simple terms, the answer is no, isn't it? It's PHribbon is not there to design.
You have to decide
system per se.
Yeah, you have to decide what flow temperature you're going to use, because that actually really is more of a question for the MCS installer, because it's matched with the boilers. The radiators. The radiators have to be able to deliver the energy required to heat the house. So that it's the MCS installer who will go forward and finalize that, and then you have to agree with him that you've done that, and he's willing to say that it will all work with that lower flow temperature. And then when you've done that, because that's a decision really rather than a part of the design of it, when you've done that, you can put that into PHribbon just to check it will all work and see the result from there. But that's really the MCS installer, and that's why
Absolutely.
It's a criteria.
Yeah, so it's this is something that wouldn't show up in your PHribbon calculations, but is bound into the overall certification process. And
exactly.
That's what we really want to kind of emphasize there. So there was also questions about in the modeling process that you've undertaken about airtightness and what assumptions. Now, it's worth here recognizing that the standards that we're talking about, step 1 does have a target for the airtightness. So that would logically be the value that would have been assumed in the in the PHPP models for step 1, for instance.
So the question was about air tightness.
Yes.
Sorry, can you just say that again?
So, but well, basically, when you were modelling the buildings, what assumptions did you make about the air tightness? Obviously, the base case, we might make a broad assumption, but which could be made more accurate if there was a blower door test undertaken, but there's not a requirement of the AECB retrofit standard to do that necessarily.
I took pretty much worst case, a typical or worst case scenario. So it just about met the criteria, which in this case, for the step-by-step is 5 meters cubed per meter squared per hour. And then for the future scenario, that would be the carbon light retrofit. That's this middle column here. It was 2. So I assumed it would be about that. People would just about meet it.
Yeah.
The existing one, I think was 15. So not very good, but probably.
No. I mean,
but
12, this really talks to the value of doing your own models, for your own building and using as much information that's available as possible. And if you can have a blower door test done, then you'd obviously be able to get a much more accurate or representative, I should say, understanding of the building performance. So that also one of the questions arose was, can the retrofit standard be used on non-domestic buildings? Yeah,
no reason why it can't.
Yeah, no, exactly.
Equally apply.
No, all of the same kinds of physics apply. We might just need to think about it in the appropriate way. My little look at my list here. There's a question about what is a PAS, so the publicly available standard. I did address that one in the chat, but hopefully we've addressed that one adequately. There was also a question relating to the difference between the carbon light retrofit and EnerFit, and what are the differences? And I think you flagged them quite clearly. You really, in terms of looking at anchoring in the use of a heat pump if you're going down a step-by-step approach, because that reduces the carbon emissions, but tailoring that, should we say, by taking into account the cost, life cycle cost in terms of energy bills, and then also recognizing the whole carbon side of considerations there. But one of the other factors that we can also talk to is the difference between the space heating demand target for the AECB the carbon light retrofit versus EnerFit. And
so EnerFit would be 25 kilowatt hours per meter squared per annum, and carbon light would be, well, it's 40 for a new build, 50 for a full retrofit, and we don't have a set target for the step 1 because they probably won't have really done any insulation to speak of.
Yeah, but it's also working. It's really that one whereby you're doing the major step, which is reducing the carbon emissions by introducing a heat pump as a technology there. So so you wouldn't necessarily have changed the space heating demand as in the heat of the heat loss of the building.
Not appreciably.
So it's not necessarily a useful point of reference in that respect. Yes, and we've got to recognize here that, of course, heat pump installers come in all flavors, so there are both men and women
and one of the things that
installers and certifiers and everything else as well.
And one of the things that the AECB brings together very well is it brings together a lot of very important good design features and brings them into the same standard. And that's not just from the single point of looking at low energy or low carbon. It actually broadens out a little bit more for all sorts of things for good design, like the cost comparison. We do want people to be able to pay for it in a way that doesn't seem like they're being they're a little bit paying a little bit more for it.
Yeah. One of the things that we can also talk to for step 1 is the importance of whilst we are introducing a heat pump, it's not the sole measure, and it's not, and we're not paying. It's not just a case of paying attention to getting the bills down. There's that key requisite quality whereby we're thinking about the health and well-being of the people living in the properties, and also mindful of the fact that it'll be retrofitted at in stages as a future, in the future. So getting the air tightness in place, getting ventilation systems strategies in place, so MEV or MVHR, to suit the later improvements, means that we're preserving good indoor air quality throughout the duration of the retrofit process, and therefore safeguarding the health and well-being of the occupants and the users of the building.
Yeah.
So again, it's that one. There's a holistic approach to the retrofit standard, which is thinking about people's health and well-being, reducing carbon emissions, as opposed to just focusing on reducing carbon emissions and failing to kind of think about people's health
and then not having the other aspects of good design. Yeah,
absolutely. And then of course, there may be other interventions in terms of improving insulation, replacing appropriate windows and things, but seeing how that can also fit into the broader life cycle of the project.
One thing I haven't mentioned, I wonder if people had asked this. One thing I haven't mentioned is that we initially thought that the use of a heat pump, it would have to be a larger heat pump at the step 1 stage, because you haven't insulated the house, so the heat demand is going to be quite large. We thought that might mean that you were kind of locked in to having a heat pump, and having a larger heat pump, and you couldn't replace it until you couldn't actually replace that heat pump until you'd done the retrofit. Sorry, you were locked into using the larger heat pump, which meant that you would it would make it difficult to do the full retrofit. So does it make you completely stuck, for example, using an inefficient heat pump? Well, the thing is, it doesn't actually mean that you are stuck. You can still, if you do a retrofit before that first heat pump is finished its life, it'll still work fine. And this summarizes some in-depth conversations that were a group of us were having with Alan Clark, who's an expert in services design. Well, he's a services engineer and a very respected expert in that. And he was saying that the step 1 allows you to you can still reduce the temperature, and you can still modulate down in order for that scenario to work really well. So it doesn't limit you. What we were trying to say here is having that larger air source heat pump for step 1 doesn't limit you to wait until you can do the full retrofit. You can do it sooner and still retain that heat pump, and it will be okay.
Yeah. So just one query that's come in about, as a homeowner, who do you, I just noticed that Andy's answered the same question as I was just answering, but basically who can certify these projects? And there's a list of certifiers on the AECB website.
Yes, it's no longer done through self-certification. We have a part of the QA of this is that we now have qualified certifiers who will go through this, and part of that is because for retrofit there are many more risks, and with new build you can tend to screen out some of the more difficult risks. Well, people have qualification for that anyway, but many of the people that are certifiers, they can certify through their Passivhaus training. They can certify new build, but they would require extra training in order to be able to certify retrofit.
Yeah,
that requires quite an in-depth course.
Yeah,
that enables them to spot things which you may not spot.
Yeah, and so it's I think that we've got the scenario there where yeah, having the right qualifications, understanding and experience all kind of fits into that. One of the queries that's, or the observations that's been made is that, change, should we say, the step one is measure of requiring an air tightness of less than 5 is could require in its own right some quite considerable retrofit. Now, I think that there are swings and roundabouts to that. 5 is not should we say very impressive relative to other performance criteria or performance standards for air tightness that will ultimately be required. It's a good step in the right direction, but it's a key variable in terms of getting helping to take steps towards controlling the ventilation in a suitable way, so you get good indoor air quality, as in you put air in the right places and you can remove air from the right places. It's also one of eliminating drafts and discomfort, which are kind of a very large part of how we perceive the world, should we say, from a thermal perspective, a comfort perspective. And that is another kind of key consideration in that respect. In terms of actually practical delivery, there are certain, depending on, it's going to be property specific. If you've got an older property, then dare I say, if it's got solid wall construction and wet plaster walls, it's going to be easier to achieve the air tightness target than it may be if you've got a 1980s dot and dab plasterboarded property. So all of these things need to be considered, and that's why having the right professionals on board to help guide you through the process and understand the systems of where we stand and how to deal with things. Just noting the time, it's 1 o'clock, just after 1 o'clock. So we've really reached the end of our time limit here. There've been absolutely tons of questions made. Hopefully we've managed to address as many of them as we have within the time available. If not, then no doubt we'll be able to take those questions on board, and Tim will be able to do a refresh of this presentation at a later date, addressing many of the pertinent and salient points that are kind of frequently asked questions, should we say, that we've noted today. So all that remains is for me to say thank you very much, Tim, for your time and your contribution today. It's been very illuminating, very useful, and I hope that everybody else that's here has also found it equally beneficial. We've still got 160 people here. It peaked at around about 200, so there's been plenty of fascination with everything that's been discussed.
Well,
thank you very much, and yeah, we'll say goodbye to everybody now.